All right. So last time, let's see, we finished off that integrability thing, whatever. I think I left a couple of hints. I guess I can just check what I said, right? But I think I left off a couple of hints talking about differentiability and the fact that differentiability is kind of nasty. Yeah, see, there it is. Show differentiability is not preserved. So we've got this thing here. So maybe let's start with that. Let's show that you can have a uniformly convergent sequence of differentiable functions, which is not differentiable. And then we'll state a nice little theorem here that tells us sort of what we can do to put things together. So, example. So let's show that these functions, let's make them R. It doesn't matter, R to R. Converges uniformly to the absolute value of X. Okay, and that will show, right, that differentiability isn't preserved because the left functions, the functions on the left are always differentiable, right? You can differentiate them. You'll get like a 1 over square root thing, but that denominator will never be 0 because you're taking X squared plus a strictly positive number. So the left-hand side is always differentiable, but the right-hand side we know obviously is not differentiable at 0, right? So yeah, uniform convergence is not going to preserve differentiability. The proof of this one isn't too bad. So let's see, basically what I want to say is the following. Oh yeah, so recall, we have subadditivity of the roots of really of any root, but subadditivity of the roots is pretty nice. So what that means is the square root of a plus b is less than or equal to the square root of a plus the square root of b. That's sort of like a math 102 proof. It's not too hard, right? On the left-hand side, add, you know, the, what do you want? 2 times the square root of ab, and then you can factor it and yada, 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 right? So you get that. So if we use this, what are we going to get? We're going to get 0 is less than or equal to x squared plus 1 over n squared is less than or equal to the absolute value of x plus 1 over n. Right, so in particular, 0 is less than or equal to x squared plus 1 over n squared minus the absolute value of x is less than or equal to 1 over n. And certainly, you know, we can make that thing now converge by choosing little n sufficiently large, and this doesn't depend on x, right? So it converges uniformly. So let epsilon greater than 0 be given. Maybe let's give this equation a name. Let's call that star. And choose, right, n in n such that 1 over n is less than epsilon, then plus 1 over n squared minus the absolute value of x, which you've already said, right? This is the math we did above. And in fact, this number is positive because the square root of x squared plus 1 over n squared is bigger than the absolute value of x. So this is going to be less than or equal to 1 over n, which is less than or equal to 1 over capital N, which is less than epsilon, if n is greater than or equal to n, like so, right? So great, it converges uniformly. All those functions are differentiable. Their limit's not differentiable. All right, so uniform convergence, even though it does lots of nice things, preserves continuity, preserves boundedness, preserves integrability, and preserves antiderivatives, does not preserve differentiability. And in fact, the situation is worse. Okay, so the situation is worse in the sense that, well, here we might say, okay, fine, it didn't converge to something which is differentiable, but what if it does, right? Maybe we just chose a bad set of functions. What if it does converge to something that's differentiable? Can I guarantee then that my derivatives converge uniformly? And the answer to that is also no. So let's show that. And again, let's just take the whole real line. What do I want here? X maps to, oh, Fn sine nx or cosine, it doesn't matter. Converges to the zero function uniformly. Okay. And then I'll show you what's wrong with this in a second, and I'll tell you why uniform convergence, why we wouldn't expect it to preserve even, not just differentiability, but even that if you do converge to something which is differentiable, because the zero function is certainly differentiable, why nonetheless we don't expect the derivatives to also converge. Okay, so again, this proof isn't too bad. It's basically sort of like a squeeze theorem argument. And what we're going to say is, well, since, -1 is, or let's say, no, sine. So because sine is always between plus or minus 1, this is going to let us bound, or sorry, not nx, just n. This is going to let us bound this function here, right, fn. And again, right, no x's, because the only place the x occurs is actually in the numerator, in the sine nx portion, and we're going to get rid of it because we're going to replace it by plus or minus 1. So we're going to get -1 over n is less than or equal to sine nx over n is less than or equal to 1 over n, right? i.e. sine nx over n. And you know what? Let me put the -0 here. Obviously, you don't have to put that, but kind of just to, be clear that one of these things is fn and the other is f. That thing's always going to be less than or equal to 1 over n. So just as above, right? Again, if we say, let epsilon greater than 0 be given, and take n in n to be, typical trick, 1 over epsilon. Then if n is greater than or equal to n, sine nx over n less than or equal to 1 over n less than epsilon, right? And the choice of n there doesn't depend on x at all. So again, it's uniform. And again, so look at this, right? So what we note here is that the derivatives, again, not well behaved. So if fnx is sine nx all over n, then the derivatives, okay, what are we going to get? So we're going to get, I think, just cosine nx, right? And that doesn't converge as n goes to infinity. Okay, it doesn't even converge pointwise to anything, let alone uniformly. Right? Because it just starts oscillating faster and faster and faster. If it were to converge, it'd somehow have to converge to like a solid block. And that's obviously, that's not going to happen. So that thing doesn't converge, not even pointwise. So here we have it, uniform limit of differentiable functions, which converges to something differentiable, but their derivatives don't even converge to each other pointwise, right? So again, I think sort of the best way to see some of this is to graph it. And me being foolish did not set this up ahead of time, but that's fine. Let's, we'll do it live, right? So what do I want? Yes, this is what I want. All right, so let's do the first function first. So what was it? It was the square root of x squared plus 1 over n squared, right? And let's just modify this. Let's go to like 20 or something. All right, so hopefully everyone can see that. And yeah, so you can see this thing is smooth, right? It doesn't have any cusps or anything in it. There's nothing kind of crazy there. But as I let n get really, really big, ooh, maybe let's make this even bigger. Let's go to like 200 or something. Okay. As I let n get really, really big, it does seem to kind of be, that point is starting to actually sort of become a cusp, right? And it is going to become the absolute value function. So even though here n is equal to 200, this function is technically smooth, if we zoomed in enough, right? So it is smooth if we zoom in enough, but as we let n continue to get even and even bigger, that's going to become an actual point. So that's why we expected not to preserve differentiability, in the sense that you can approximate a non-differentiable function by a differentiable function arbitrarily well, right? Or in this case, at least we can. So we're sort of not surprised by that. And yeah, we really wouldn't expect differentiability to be preserved. Now, for the other one, the sine nx, and again, let's put some steps in here. I don't think we need to go too high for this one. All right. So here's our typical, just sine x. And then as I increase n, so two things happen, right? The first is that the function begins to oscillate faster and faster and faster. Okay, so hopefully you can see that. So here, for example, it looks like we hit an entire period in about 1, right? So instead of being 2 pi, our period now is just a little bit bigger than 1, as we would expect, right? It would be 2 pi divided by 6. And so we begin to oscillate quicker, but also our magnitude shrinks. And so this is why we're converging uniformly to the function 0, right? You can see that the magnitude of the function is actually squishing down and is getting really close to 0 and isn't leaving this sort of epsilon tube of 0. In this case, it's actually an epsilon band because we're talking about the constant function, right? So this function is converging uniformly to 0. You can see it, right? It's squishing down. But as n goes off to infinity, it begins to oscillate faster and faster and faster, right? Even though the magnitude is getting smaller. And if you think about those oscillations, the fact that you're sort of rapidly moving, even though your magnitude is small, the fact that you're rapidly oscillating back and forth means that your derivative is actually fairly large, right? It, relatively speaking, ends up being quite large, because you have to, if you're like going up very quick and then going down very quick and then going up very quick and going down very quick, this has an effect on your oscillation, right? So it is, for example, possible for functions to have horizontal asymptotes at 0, but their derivatives explode off to infinity precisely because they do this sort of thing. They sort of oscillate quicker and quicker and quicker as you go to 0, but their magnitude shrinks such that they converge to 0. So that's the same thing we're seeing here. Magnitude is shrinking, gives us uniform convergence, but the massive and rapid oscillation is preventing the derivatives from converging. Okay, so that's the sort of thing that's happening there, and that's why we really wouldn't expect differentiability to work. It's just not, differentiability is not well behaved. Now, integration is sort of a different story, right? Integration is generally a smoothing operator. Things sort of get nicer, they don't get less nice. That's not true of differentiability, right? Differentiability is typically differentiating things makes them worse, right? Not better. You get things like, the cubed root of x, which is a perfectly nice function, but you differentiate it and you get something gross, right? You get something which is actually like a vertical asymptote there. That's no good. So generally, not a good operation. And in fact, this ends up being, kind of super important if you go and you study quantum mechanics and in some cases, partial differential equations in general. The fact that you can take a bounded function and when you differentiate it, you get an unbounded thing is actually a real big pain in the butt. And mathematically, you have to do a lot of weird stuff in order to correct for that. Okay, so there's kind of no way around that. All right. So there is a theorem here. I guess if I'm going to state, I can state this theorem, but I can't really prove it unless I do the following. So let me maybe I was debating on Tuesday whether or not I was going to talk about some of this stuff. I think I have time, so let me just kind of do it. I'm going to have to do it quickly though. And I think you're going to have to take some of what I say on faith just because we didn't do it back in the day because it would have taken too long. Okay, but it's not too hard to find treatises on this. So here, let me just quickly state a theorem. So theorem, every Cauchy sequence is convergent, and that's just Cauchy sequences of real numbers, right? So if an is a sequence of real numbers, okay, not of functions, then AN is Cauchy if and only if it is convergent. Okay, so we know lots about convergent sequences. We don't know much about Cauchy. I think I made you do one assignment problem on Cauchy sequences, right? But it turns out you can prove that all Cauchy sequences converge. That is an intense proof. The reality is that it probably takes 3 or 4 major theorems in order to prove this, which is why we didn't do it. But if you believe me that this theorem is true, then we can move forward, okay? So every convergent sequence is Cauchy. That's not hard to prove. Every Cauchy sequence is convergent. That is hard to prove, but it is true, okay? And look up the proofs. The proof is interesting, but it's also the sort of thing that is so ad hoc. Like the proofs are so specific that their techniques don't generalize well to sort of treating other things, which really just sort of makes it not worth our time when there are other things that we want to talk about. But go check it out, especially again, if you do have my book, it is in this section on like convergent sequences, and it does walk you through that proof. And then the exercises walk you through another proof because there's multiple proofs. Okay, so the only thing I want you to internalize there, Cauchy and convergent effectively are the same thing. Now, the great thing about Cauchy sequences though, is they allow you to tell that something converges then without actually knowing its limit point, right? If you can show that a sequence is Cauchy, you don't have to know what it converges to. You just have to know it's Cauchy, and then you know that it's convergent, right? That's really, really nice. Okay, so then what we can say is definition. We're going to define what it means for a sequence of functions to be uniformly Cauchy, right? So if Fn is a sequence of functions, we say that it's uniformly Cauchy and of course there's a pointwise notion too, but who cares, right? Because pointwise sucks. So it's uniformly Cauchy if it's a Cauchy sequence, right? So if for every epsilon greater than 0, there exists some n such that for every m and n greater than or equal to n, and for all x and I, so many quantifiers. Like that, right? So it's a Cauchy sequence, but it's uniformly Cauchy. So again, it sort of doesn't depend on x, right? The choice of capital N doesn't depend on the particular point that you're picking, okay? So that's sort of a nice thing. And then we get, well, a sequence is uniformly convergent if and only if it's uniformly Cauchy. Okay, so a sequence is uniformly convergent if and only if it is uniformly Cauchy. Okay, this one isn't hard to prove if you assume the first theorem. Okay, because basically what you do is you say, okay, well, let's actually, if you're uniformly Cauchy, you're pointwise Cauchy, right? And if you're pointwise Cauchy, then at every, like if you put in one element of x, and you actually just, you don't look at the function, you just look at Fn of x, right, as n goes to infinity. That is a Cauchy sequence of real numbers and therefore convergence. So what you're going to do is define f, the limiting function in this way, right? Maybe as just sort of like an outline, right? So define f of x to be the pointwise limit. And those always exist because the Fnx's are Cauchy as real numbers. And then just show that, it converges to this uniformly, which is just, it's like some sort of epsilon over 2 argument, right? And then show Fn converges to F uniformly. This is an epsilon over 2 argument. Okay, so it's not too hard. It's not terrible at all to do. Okay, but you kind of have to assume the first one. So the first one is terrible, right? The first theorem here at the top, that is terrible. But if you believe that, then this one isn't too bad. Okay. So, all right. Now the theorem that I want to state in terms of differentiability, I don't know if I'm going to necessarily go through it, especially if I want to get to like the Weierstrass M test. But the theorem is basically this. So the theorem is if Fn converges to F uniformly, Fn and F are differentiable, and the Fn primes converge to some function for some function g, then g must be the derivative of f. Okay. So we've got a whole whack of hypotheses in order to make uniform convergence of differentiability be preserved. Okay. So we have to assume Fn converges to F uniformly. Everything there is differentiable. And then the derivatives also converge uniformly to something. And you don't care what that something is, as long as the derivatives themselves converge uniformly to something. And that's something that we were missing in each of the previous two examples, right? So in the previous example, or in the first of the previous examples, not that one. In this one, we didn't even have that they converged to something that was differentiable. That is a hypothesis in our new theorem. In the sine nx one, we needed that the derivatives also converged uniformly to something, and we don't have that because they don't even converge pointwise. Okay, so in this theorem here, the f's have to converge uniformly, everything has to be differentiable, and the derivatives have to converge uniformly. If that happens, then whatever the derivatives converge to was actually the derivative of little f. Okay, and I don't think like, you're like, wow, that's a lot of hypotheses that we need to include just to make this happen, right? And yeah, it absolutely is, which is why, it's not, this ends up, it doesn't show up a lot, but this theorem shows up enough that it's, it's not worth sort of throwing out. I'm going to outline the proof and then like sort of do the rough work. And then I'm going to let you sort of finish it off. It's not, right? Just like when we were doing epsilon delta is how I do the rough work and say like, you can actually write up the proof itself. So basically what we're going to do, what are we actually trying to prove here? This is the thing we're trying to prove, right? We're trying to prove that whatever the derivatives converge to uniformly was actually the derivative of f. So what we want to look at is we want to look at this thing. Right? So the left-hand side, you're going to take a limit as, y approaches x, and then, that will end up being the derivative, and we want that thing to be the right-hand side. So this is, this is what we're doing. And we're going to, look at what happens when x minus y is sufficiently small, right? It's less than some sort of delta. So if x minus y is less than delta, and this is true, that will tell us, right, because the left-hand side is the definition of the derivative, that will tell us that the derivative of f is equal to g. Now we're going to do our typical sort of add and subtract things that we recognize until, we get something that we want. So let's write this as f of x minus f of y divided by x minus y minus fn of x. Is that what I want to do? Pretty sure it is. Let me just double check here. Yes. Okay, plus y, x minus y, minus, I think I want here f prime. Yeah. Plus, oh no, x, because I'm doing it in x's. Like so. Okay. You're right. Yeah. Less than or equal to, because I did use the triangle inequality. Okay. So this thing, we're good to go, right? Because we know each of the fn's are differentiable. Differentiable. Right? So we know the fn's are differentiable. Boom, I can make that thing as small as I want. This, no problem, because we know the fn's converge uniformly to G. Or fn primes, rather. Right? It's this thing that isn't obvious. So that's the sort of thing that we have to play with. And that's going to be the tricky thing. So the solution to that is actually going to be to prove that that thing is uniformly Cauchy. Because if you can prove that that thing's uniformly Cauchy, then you'll get that this thing converges. And the thing it has to converge to is the left-hand side. So let's basically, we want to argue that this thing here is uniformly Cauchy. This will force it to converge to the left-hand side, and we'll be done from there. All right? So, we want to show that fnx minus fny divided by x minus y is uniformly Cauchy. Okay, y here is fixed, right? For fixed y. But any fixed y. Okay, so how do you do that? Well, again, I'm just going to do the rough work here and make you sort of do the rest. And I'm going to rewrite this as fn minus fm of x minus fn minus fm of y divided by x minus y, right? And then, well, each of these things is differentiable on the interval xy and is continuous, certainly on the closed interval. So by the mean value theorem, well, here, maybe let me write it like this. By the MVT, right? That's equal to fn prime c minus fm prime of c. But we know that the fn primes converge, so I can make this thing less than epsilon. But the fn primes are uniformly Cauchy, right? Because they converge, they're uniformly Cauchy, which means this thing can be made less than epsilon over 3 or whatever you want. So that means that this sequence is as well. Is also uniformly Cauchy. Okay, and that's it. Now you have that you control. Here, let me zoom out here. So up here at the top of the screen, you've got these three things. You can control all three of those things. They all converge. You can make them all as small as you want them to be. And boom, you're good to go. Right? So just make each of them less than epsilon over 3 or something like that. You add them all together And you get it, right? Epsilon over 3 plus epsilon over 3 plus epsilon over 3 is epsilon. So you get the result that you want. So you can see here, even just writing out the rough work is a little bit of time and energy. Plus, I did, again, sort of only do the rough work to show that the sequence was uniformly Cauchy. Again, specifically, you should say, let epsilon be greater than 0 and choose n sufficiently big that the Fn primes are uniformly Cauchy. Well, that same n works for this sequence. And then apply the mean value theorem, yada, yada, yada. And you can see being uniformly Cauchy is very nice here. The uniform is important because that C must occur between X and Y, but it doesn't matter where it occurs because you're uniformly Cauchy, right? So you know that this inequality right here, when you want to make that less than epsilon, it's going to hold for all X's or all Y's or all C's, right? It doesn't matter. It holds for everything. So being uniformly Cauchy here, really nice, really important, and lets you kind of not have to worry about the fact that C might be inside of that interval and not exactly some point that you're after, right? If you only had sort of pointwise, this would be a little bit trickier. Okay, so that's how you prove that one. So let's get to let's start series of functions. That's kind of as far as we want to talk about in terms of sequences of functions. But now we're going to start talking about series. So the big expose on series is going to be next week. For us, let's just start with some definitions and maybe hopefully get to Weierstrass. And with me now doing Cauchy, even if we don't get to today, I'll talk about Weierstrass next time. So definition, it's exactly what you expect it to be, right? We're going to look at a series of functions. We'll determine whether it converges by looking at its partial sums, and we'll say that it converges uniformly or pointwise if the partial sums converge uniformly or pointwise, right? So if Fn from I to R is a sequence of functions, the partial series, or do I want to just define straight to its infinite series? Let's just define the partial sums. So its partial sums are Sn is the sum. Let's start at 1 to n fk like this, okay? So now we will say that this converges uniformly if the partial sums converge to something uniformly, and it converges pointwise if they converge to something pointwise. So if there is, or maybe we say that the sum from k equals 1 to infinity, fk is s for some function S mapping I to R uniformly if Sn converges to S uniformly and to pointwise. We're not going to be interested in pointwise, but you should know it exists. Pointwise, like so. Okay, so the infinite series is equal to S uniformly or converges to S uniformly. Either would be fine. Everyone will know what you mean. So you can say it's equal to S uniformly or converges to S uniformly if the partial sums converge to S uniformly, right? So it's the exact same notion of series that we would have for real numbers, except now, of course, everything are sequences. Now, one of the things, again, we lose here is that we don't have monotone convergence theorem, right? Because we don't have a notion of an increasing sequence of functions. We don't have a notion of a bounded sequence of functions. And the MCT is so critical to proving a lot of our convergence results that, oh, we're in trouble. And the situation is even worse. It might turn out that the series converges to a function, but only on like some subinterval of its domain, right? So this is something that we're really going to have to talk about and think about next week. We're not going to talk about it this week, but it turns out you might not even get global convergence. It might be the best that you can do is local convergence, right? And so that's something that we're going to have to worry about. And yeah, we're going to have to figure out, where do these things actually converge? It might not be everywhere. It might just be in some small domain. And then the situation gets much worse after that. So things are getting, well, okay, but what would you do? Because we don't have an order on we don't have an order on functions, right? Like, we don't really have a good notion of increasing or decreasing. Like, what does this mean? Not as points, right? You might be able to do something like that. It's not clear to me that that's useful. And then even if you do have a notion of order, which again, you could define that would be fine. Even once you do have a notion of order, it's not clear to me. You don't have a notion of the soup of the sequence of functions. Do you know what I mean? Like, you'd have to do some sort of double soup. So like, it's going to get, you try it, like, see if you can make an MCT for functions. I think that'd be really cool if you manage to get something. Yeah, but then you have to now also do that for all the, like, every n, right? So it's not enough to do the soup of fn, but now you have to do the soup of the soups of fn or something like this, right? And then they all also have to be uniformly bounded. So not just bounded, but also uniformly bounded. So you might get somewhere. And then the limit superior is sort of like a different thing, right? It's just sort of makes your life a little bit easier if you're dealing with functions that don't behave exactly the way you want to early in your sequence, but do behave better later in your sequence. That's really what the limit superior is for. I don't want you all to worry about the limit superior too much. It's a little bit messy to work with, but yeah, exactly. So, but try and throw as many conditions at the MC. Like, if you want to make the MCT work and you need really stringent conditions, that's fine. Throw them in until you get a theorem that you think works out. It's going to be a little bit messy because now you've got like an MCT basically for every point almost, right? That's sort of what you're doing, is you're almost doing it a point-wise thing. And then that's not even clear that will converge to something globally, but maybe it'll work. You might be able to do something like that. Basically like a pointwise MCT that you stitch together might even work, but then is it uniform? Maybe not. And then we'd have to change it and find a uniform thing. It's tricky. Okay. Yeah, all right. So fine, we've got some notion of convergence here. Next week, we're going to see a ton of examples of these things. I want to get Weierstrass out here. So the first thing that we need is to translate the Cauchy condition into a partial sum condition. So we've got theorem. So if Sn, let me just be a little bit lazy here and not, so this is, a partial sum of some sequence of functions that it exists, is a partial sum then Sn converges uniformly if and only if for every epsilon greater than 0, there exists an n in n such that for all m greater than or equal to n, I guess, greater than or equal to n, k equals n to m is less than epsilon. Let me just double check that I stated that exactly how I wanted it to. I use m plus 1. Okay, fine. We'll use n plus 1. Yeah, it should be n plus 1. Okay, and this is just the Cauchy condition. There's nothing to do here. So proof, right? Note that m minus Sn is the sum from k equals 1 to m minus the sum from k equal 1 to m n plus 1 to m. And so this thing here is just the same thing as these, like this Cauchy. This condition is precisely the statement that the SNs are uniformly Cauchy, right? So the theorem statement is that Sn is uniformly Cauchy. Right, so again, we know you're uniformly convergent if and only if you're uniformly Cauchy. This theorem says, hey, your partial sums are uniformly convergent if and only if this thing is true, but that thing is just a rewriting of uniformly Cauchy, right? So again, this is just that theorem rewritten in the language of partial sums, right? This is the uniformly Cauchy condition for partial sums written down here. Okay, so here's the crazy, like here's the Weierstrass M test. It's surprising that this works. It's even more surprising how easy this proof is. So this is the Weierstrass M test. Okay, and it goes as follows. So suppose right, it's basically one of our, what is the thing in the absolute value? Which absolute value? Like, oh, sorry, that should be another FK. Yeah, just another FK. Cool. Okay, so suppose Fn is a sequence. Oops, it's not yellow. Of functions, and for every n, there exists a bound. Do I want this? Yeah, let's say this is greater than 0. Such that okay, so all of your functions are bounded, right? That's just what this statement is. And again, they can be bounded by different things. They don't have to be uniformly bounded. And in fact, you don't want them to be uniformly bounded. If your bounds converge as a series, then your sequence converges, or then your series converges. Okay, so if converges uniformly. Yeah, that is cool. Proof is so easy too. Okay, but yeah, if you can bound each of your functions with bounds that converge as a series, then you converge uniformly. Proof. Well, let's let epsilon greater than 0. Basically, what we're going to do is we're going to show that this is the partial sums is uniformly Cauchy, right? So let's show that Sn is uniformly Cauchy, right? I.e., we're going to show that that condition above is true, right, from my previous theorem. Now, so let's say let epsilon greater than 0 be given, since the series MK converges, its partial sums are also convergent and therefore are also Cauchy. So let epsilon greater than 0 be given. Since the sum from k equals 1 to infinity mk is convergent, its partial sums are Cauchy as well. So there exists some n in n such that for all m greater than or equal to n greater than or equal to n, right? So again, right, like that condition on series, we didn't state it when we were doing series, but obviously it also applies for series, right? Because today is really the day we're talking about Cauchy stuff. So that condition also holds for just series of real numbers where, you take the sum, you take this thing to be less than epsilon, right? This is really, again, the definition of the partial sums of just real numbers, not of sequences, being Cauchy. So yeah, okay, they're convergent, therefore they're Cauchy, therefore we can make this happen, right? And boom, we basically have it done now. Right, so thus S m if m greater than or equal to n greater than or equal to n, well, less than or equal to. Right, and I guess, yeah, all those numbers are positive, so we don't actually need the absolute value there. And that's it, we're done. How easy is that? Right, super easy, insanely easy. It shouldn't have been that easy, but it is. Okay, so this is, one of our only convergence tests for sequences of functions. Now, I'm not going to get a chance to actually do this, but here's a quick little exercise that you can practice. Let's start at 0 here. It doesn't matter. 1 over 2 to the k cosine 3 to the kx. Okay. Should be here. N is, oh, m is the bigger one. You're right. Thank you. Good catch. Good catch. All right, m is the bigger one. Yeah, very good catch, Nicole. Thank you. And there's one more in the yes, you're right. Very good catch. It would have been easier. I should have just switched them. I should have just switched them here, right? It would have made my life so much easier than having to change all the rest of them. Oh well, whatever. Hindsight's 2020. Okay. I want you to check that this converges uniformly. It's very straightforward now by the Weierstrass M test. Okay, we're a little bit over. This converges uniformly. I want you to graph this and tell me what it looks like. Okay, just plug this into Desmos. Obviously, you can't do infinity. Do like 10 terms or something, and see what exactly this sum looks like. And you're going to see, oh, this is a nightmare function. This is the worst thing that I could possibly imagine. And yeah, this will be a nice example. We'll do this first thing next time just so we can talk about it. But yeah, this is an example of an everywhere continuous, nowhere differentiable function. Yeah, exactly. Yeah, the fact, like the completeness of the real numbers, that theorem is precisely every Cauchy sequence converges, right? Yeah. Okay. But yeah, this green function, everywhere continuous, proof is trivial, right? Because look at the partial sums. The partial sums are all continuous, right? So if this converges uniformly, its limit is also continuous. This function is everywhere continuous and is nowhere differentiable. If you graph this thing, it looks like there's an infinite number of like jaggedy mountain thingies in it. Okay, so plot this function in Desmos, everywhere continuous, nowhere differentiable. And we'll talk about that like first thing on Tuesday, because it's a quick proof, right? It's very easy to show this thing converges and therefore that it's continuous. But like I said, I want you to actually go plug that into Desmos and see what is happening, because we're oscillating really, really quickly, but with smaller and smaller magnitudes. But that doesn't matter. Basically, what we're happening is we're guaranteeing that at every point we're oscillating so quickly and in every possible direction that you just get these like, these jagged sort of corners and curves everywhere. Right, and that kind of screws everything up for us. Okay, so it's a nice, fun little example. All right, everyone, that's going to finish it today. I'll post some test information for you on Friday, but basically everything up to and including today is what your next term test will cover. Yeah. Let me just unrecord.